Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to build a support vector machine using the iris dataset. Even before I proceed to demonstrate how to build a support vector machine using the iris dataset, may I request you to subscribe to my channel, also like and share my videos. Let me begin by introducing to you the dataset that I'll be working on. This is the very popular iris dataset. As you can see here, there are 6 columns in this particular dataset. The first is the flower ID. Then we have flower characteristics like sepal length, sepal width, petal length, and petal width. Each of these 4 variables is measured in centimeters. The last variable that I have is the flower species, the species of the flower. What is the sample size in this dataset? When I go to the last record, it says 150. So what we have is the flower characteristics of 150 different flowers. When you look at the first record, it represents a flower which has 5.1 centimeters of sepal length. The sepal width here is 3.5 centimeters. Petal length would be 1.4 centimeters and the petal width would be 0.2. This is the Setosa species of flower. Let me use the drop-down menu here. I'll be using a filter condition to show you the 3 different species of flower. In the target variable, you can see Setosa, versicolor, and virginica. These are the 3 different species of flower. Hence, this would be what is called as a multi-class problem, because we have 3 different species of flowers. The goal in this case would be to predict the species of flower based on the input variables like sepal length, sepal width, petal length, and petal width. Let us go ahead and build a support vector machine using Python. Let's begin by asking a simple question as to what is support vector machine. By the way, this is the Jupyter Notebook. For those of us who are not familiar with Jupyter Notebook, this is how the interface of Jupyter Notebook looks like. It is an interface which is popularly used when we build machine learning models in Python. So what exactly is the support vector machine? Support vector machine is a supervised machine learning algorithm. I repeat, this is an example of a supervised machine learning algorithm. It is used mainly for classification and regression tasks. If a support vector machine is used for classification, it is called as a support vector classifier. On the other hand, if a support vector machine is used for regression-based problems, it is called as support vector regressor. Let's now ask the next question. Where is support vector machine used? Support vector machine can be used wherever we use some of the other machine learning techniques like logistic regression, decision tree, linear regression, naive-Bayes classifier, etc. Let us say you have run a logistic regression model and you have got a very low percentage of accuracy. Now you can run a support vector machine, look at the accuracy obtained from support vector machine, compare it with the accuracy of the logistic regression model or the decision tree model. If the accuracy obtained by the support vector machine outperforms the accuracy obtained from any of the other classifier, then you can go ahead and declare that support vector machine is the champion model. So it's a great tool for comparative purposes. Support vector machine is more suited for a few cases. In case the data is very sparse, then you can use support vector machine. Secondly, if you're dealing with high dimensional data, there again support vector machine comes into picture. Imagine a case wherein the number of dimensions that you're working on would be 200. So if you have 200 columns and merely 150 records, That's a classic example of high dimensional data, and support vector machine works very, very well when we have high dimensional data. Thirdly, support vector machine is also used for text classification problems. Fourthly, when there is a nonlinear pattern in the data, we can use the support vector machine. In case you have a linear relationship, we can go ahead and use the logistic regression model. On the other hand, when there is a nonlinear pattern, it is better that we use a support vector machine. Let's also talk about image classification. Based on the image characteristics, let's say you want to classify an image as a cat or a dog, or you might want to classify an image as malignant tumor or benign tumor. Here again, support vector machine comes into picture. Last but not the least, when the data has extremely complex patterns, you can go ahead and use support vector machine. With this background about the algorithm, let us now go ahead and build the support vector machine. In the first line of code, as you can see here, in the very first line of code, what I'm doing is I'm importing a few libraries. In the first statement, I'm importing data sets from sklearn. Sklearn is a very popular machine learning library. In the second statement, what I'm doing is I'm importing the train underscore test underscore split function from sklearn.model selection. Why do we have to do this? We have to split the base data as training and testing, and therefore we will be using the train underscore test underscore split function. In the third statement, what we will be doing is we'll be importing the support vector classifier from sklearn.svm module. In the fourth statement, what we will be doing is we will be importing the accuracy score from sklearn.metrics. Once we build a model, we will have to evaluate the performance of the model. One of the most popular measures which is used to assess the performance of the model is what is called as the accuracy score. If the accuracy score is close to 100%, it means that the model that we have built is good. On the other hand, if the accuracy score is close to 0, it means that the model that we have built is poor. In the next statement, what we are doing is we are importing the Seaborn library. The Seaborn library is widely used for visualization of the data. It has a lot of interesting graphical options which we use for graphic visualization to create charts, so on and so forth. The same way, we have another library which is called as the matplotlib, and here I'm using the matplotlib.pyplot to create a few visualization. Last but not the least, in the final statement, I'm using the confusion metrics. I'll be importing the confusion metrics from sklearn.metrics. This is used to tell me the overall performance of the model. We'll be comparing the actual versus the predicted. If the actual and the predicted match, it means that the accuracy level is high. On the other hand, if there's a lot of mismatch between actual and the predicted class, it means that the model performance is poor. So overall, what I'm doing is I'm preparing the groundwork for building a support vector classifier as far as the first snippet of code is concerned. Let's now go ahead and load the iris dataset. To load the dataset, you can use the function load underscore iris function. You can create an object which is called as the iris object. Further, you have to save the independent variables as well as the dependent variable. The independent variables are saved in an object called as X, and the target variable is saved in an object called as Y. Let me go ahead and execute this particular command. So at this stage, I have loaded my data. I have created the independent variables as well as the dependent variable. The next step is to split the data set into training and testing. Why do we do this? The reason being, we take the data set, we split the data set as training and testing. We feed the training data set into the model. The model will learn certain characteristics, and we will be evaluating the performance of the model on the test dataset. This helps us avoid overfitting. If there is any overfitting, the problem of overfitting can be easily detected when we split the dataset into training as well as testing. So this is a good way of assessing the performance of the model. As you can see here, I'm using the train underscore test underscore split function. I have to specify certain parameters like X and Y. I have to also declare the size of the test dataset, which is 20%, which automatically means that 80% will be used for training. This will create 4 objects. The first object is X underscore train, which will have the 4 independent variables, namely sepal length, sepal width. It will also have the petal length and petal width for the training dataset. You have the 4 variables for the test dataset as well. The dependent variable for the training dataset is present in Y underscore train. The dependent variable for the test dataset is present in Y underscore test. So with this function, I will be getting 4 new objects, the independent variables for the training and the test dataset respectively. The same way, I'll be able to get the dependent variable for training and test respectively. Next, I'll have to create an instance of the support vector model. We can use the SVC function and define the kernel here. I'm using the linear kernel. There are other options as well. You have 7 different choices. Typically, you can use linear kernel or a polynomial kernel or a Gaussian kernel. You also have the option of using an exponential kernel or a Laplacian kernel. Next, you have hyperbolic or a sigmoid kernel. Last but not least, you also can specify the ANOVA radial basis kernel. If you want more information about the kernels and the parameters of the support vector classifier, let me take you to the user guide of the support vector machine. You can see here, this is the command that we can use to run a support vector classifier. There are different parameters here which is specified within the parentheses. I will not be going through each and every parameter. Typically, there are 3 important parameters that we can use when we are building a support vector classifier. Let me scroll down. You can see here, the first parameter that we need to keep in mind is what is called as the C function. The default value for the C function is 1.0. This is the regularization parameter. I repeat, C is nothing but the regularization parameter. The strength of the regularization is inversely proportional to C. This is a very important relationship that we can keep in mind. The strength of regularization is inversely proportional to C. This must be strictly positive. The penalty is a squared L2 penalty. This is one of the most important parameters that we need to keep in mind. The next important parameter that we need to keep in mind is what is called as the kernel function. Here in scikit-learn, there are different options like linear kernel. You can also specify the polynomial kernel or the radial basis function or the sigmoid kernel. The last option that you have is what is called as the pre-computed kernel. The default kernel that is used is the radial basis function kernel. As you can see here, you can look at the description for this particular parameter. It says this option specifies the kernel type to be used in the algorithm. If none is given, radial basis function will be used. If a callable is given, it is used to pre-compute the kernel matrix from data matrices. That matrix should be an array of shape. You have different options here. We can experiment with any of these kernels. Last but not the least, we have another important parameter which is called as the gamma function. While you can have a look at different parameters, I would suggest that you keep in mind 3 important parameters for a support vector machine. First is C function, second one is kernel, and the third one is the gamma function. This is the kernel coefficient for radial basis function, polynomial function, and sigmoid function. The default option that will be used is the scale option. You have two different options under the gamma function. The first is the scale option. The second one is the auto option. Very interestingly, when we use gamma equals scale, I repeat, when we use gamma equals scale, what is happening is there is an underlying formula that is used, which is the reciprocal of the product of the number of features and the variance of the data set. You can see here it is 1 divided by number of features multiplied by x dot variance. So you're taking the product of the number of features. In our data set, we have 4 features multiplied by the variance of the data set. When you take the product of this, you'll get a number. When we take the reciprocal of that number, we can use that answer as the gamma value. Now, what does this help us in? Gamma equals scale is a formula for calculating a regularization penalty that is added to the loss function of a linear model during training, which helps prevent overfitting by discouraging the model from assigning too much importance to any one feature. So the sum and substance of this is that we can use the gamma parameter because this helps prevent overfitting of the model. The second option that you can use for the gamma function is gamma equals auto. The first option was gamma equals scale, which would be using this particular formula, 1 divided by n underscore features multiplied by the variance of the data set. When you use auto as the function, it will be using 1 divided by number of features as the formula to compute a value. Now, any of these values can be used. We need to find out what is the optimal values for these hyperparameters, and that is an experimental process. Let me come back to the model that we were building. As you can see here, I'm going with the linear kernel. I'm saving it as an object called as model. Let's now go ahead and train the model using the training data set. You can see here, I'm using the function model.fit. I'm passing x underscore train as well as y underscore train. Let me go ahead and execute this particular code. The model has been fitted on the training data set. So once you fit the model on the training data set, the next thing that we need to do is we need to predict on the test data set. So to predict, we can use model.predict on x underscore test. This will create the predictions, and the predictions are saved as y underscore predict. So far, what we have done is to build a model and to generate the predictions. In case you want to evaluate the performance of the model, what we need to do is we need to use the accuracy underscore score. We will be assessing what is the accuracy of the model on the test data set. How do we do this? By comparing the actual class of the flower with that of the predicted class. Whenever the actual class matches the predicted class, we can say that the accuracy is high. On the other hand, when the actual does not match the predicted, we can say that the accuracy is low. In this case, we have used a small data set. Therefore, we are getting a high level of accuracy. The accuracy seems to be 100%. The objective of this video is not to build a very highly accurate model. The objective here is to demonstrate how support vector machine can be built in a real-time scenario. Along with accuracy, you have certain other measures which are called as precision, recall, and F1 score. You can see here, what I'm doing here is I'm importing certain important functions like precision score, recall score, and the F1 score. You can import this from what is called as sklearn.metrics. Next, we can calculate the precision recall and the F1 score for our data set. Remember, how do you calculate the precision score? The formula for precision is true positive divided by true positive plus false positive. I repeat, precision is calculated as the ratio of true positives divided by the sum of true positives plus false positives. So since we have false positives in the denominator, there is an inverse relationship between precision and false positives. If the model has a high value of false positives, precision will suffer, precision will go down. On the other hand, if the number of false positives is very less, precision score will go up. So in this sense, precision as a score is inversely proportional to false positive. A high precision score indicates a low percentage of false positives. Typically, precision score closer to 1 is preferred. If the precision score is greater than 90%, it is a good sign. We have another important metric which is called as recall score. Recall is calculated as the ratio of true positives divided by the sum of true positives and false negatives. Here again, recall shares a inverse relationship with false negatives. Since false negatives is in the denominator, in case the model shows a high number of false negatives, it means that the recall score will be closer to 0. On the other hand, if the false negatives is very, very low, automatically your recall score will go up. In that sense, recall has an recall score has a inverse relationship with that of false negative. A high recall score is preferred. If the recall score is greater than 90%, again, it's a good sign. Next, we have another important performance measure, which is called as the F1 score. F1 score is simply the harmonic mean between the precision score and the recall score. How do you calculate F1 score? We have to use a formula which is called as 2 times precision multiplied by recall divided by the sum of precision and recall would give us the F1 score. Let me go ahead and execute this particular option. What this will give me is precision, recall, and the F1 score. Let's now go ahead and print what are the values for precision, recall, and F1 score. In this case, we are getting 100% for precision, 100% for recall, and 100% for F1, which is automatically a good sign. Each of these performance measures along with accuracy should be greater than 90%. If it is greater than 90%, it's a very good sign. On the other hand, if any of these model performance measures is greater than 70%, the model is an acceptable model. Let's look at the next code here. Here, we are calculating the confusion matrix. Let me show you the confusion matrix here. You can see here, this is a matrix wherein you are comparing the actual versus the predicted. When the actual and the predicted meet, it's the right classification. The right classification are always represented in the diagonal element. You have 10, 9, and 11. 10 plus 9 is 19. 19 plus 11 would be 30. So 30 instances have been correctly classified here. A better way to show this would be by creating a heat map. What I'm doing here is I'm running a sns.heatmap function. I'm feeding the object, namely CM, which is the confusion matrix. I'm saying annotation equals true. I'm setting the parameter for CMap as well. Let's look at the confusion matrix here. You can see here, along the row, we have the true class. This represents the true species of the flower. And along the column, what we have is the predicted species. What is shown in dark blue color represents the correct classification. In other words, the diagonal elements represent the correct classification. The off-diagonal elements here represent the incorrect classification. As you can see here, 10 out of 10 Setosa flowers have been correctly classified. I repeat, 10 out of 10 Setosa flowers have been correctly classified. Next, let's look at 1. This represents the true value of 1 or versicolor flowers. There are 9 versicolor flowers, and each of these 9 versicolor flowers have been correctly predicted as versicolor. Finally, we have the true class as 2. This represents the Virginica flowers. How many Virginica flowers are there? We have 11 different Virginica flowers, and all of these 11 Virginica flowers have been correctly predicted. So this is how the confusion matrix can be used to identify the performance of the model. To have a quick recap of whatever we did, in this video, we've seen what exactly is a support vector machine. We further went on to discuss when can we use the support vector machine. We imported the libraries, loaded the dataset, we split the dataset into training and test dataset. Further, we built a support vector machine. To evaluate the performance of the model, we checked the accuracy measure. We also looked at precision, recall, and F1 score. As a last step, what we did is we generated the confusion matrix. With this, I have come to the end of today's video. In today's video, we've looked at support vector machine on Iris dataset. I thank you very much for watching this particular video. I request you to subscribe to my channel, also like and share my videos. Thank you very much once again. Have a great day ahead.